Okay, everyone, so what I want to do in this video here, I want to walk you guys through the steps for deriving the change in elastic potential energy equation. So if you remember in class, in order to do that, we did two things. We collected data, and then after that, we interpreted that data. So in order to collect the data, we began by taking an ordinary spring, and we took a force sensor. So we connected the force sensor to the spring, and we pulled the spring to 3 different points. We pulled it 10 centimeters, and we measured the value of the force at that point. Then we pulled it 20 centimeters, we measured the force at that point. And then we pulled it 30 centimeters, and we measured the magnitude of the force at that point. And then from there, we took our data and we put it in an Excel spreadsheet like this. So we put the distance stretched on the x-axis, and of course we converted centimeters to meters, and then we put the magnitude of the force at each of those points on the y-axis. And then from there, when we plotted it out, we got a nice straight sloping line that looks something like this. So it was a linear function. Now, before we analyze this further, I want to say this. On the test, you're going to be given this. You're going to be given the equation for the force of a spring, which is equal to negative kx, where it's understood that k represents your spring constant, which means the magnitude of stiffness, and x represents the distance stretched or compressed. In this case, the distance that we stretched the spring in this particular example here. Okay, so with that said, going back to our data, so remember, on the y-axis was force, and then on our x-axis was displacement or distance stretched. Now, we first begin by analyzing this slope here. The question is, what does this slope tell us? So the slope of this line, which in this case is 5.7, what does that slope mean? Well, that's easy. Slope is rise over run, or in this case, force divided by displacement, or force divided by x. So what that is, that's easy. That's the spring constant. If we take rise over run, or force divided by displacement, what we get is the spring constant k, right? Because if you take this equation here, and if you divide force divided by displacement, what you get is k. So that's what the slope tells us. The slope is equal to the magnitude of stiffness, for the spring. Now, there's something else that we can do with this data. Not only can we take the slope of this line here, but we can also take the area underneath this line. And the question is, what does the area tell us? Okay. Well, if you remember, area, in order to take the area of something, you do the opposite of slope. Whenever you take the slope, you divide rise over run. But in the case of area, you want to multiply. So in this case, you're going to multiply your y values by your x values. In this case, force multiplied by displacement. So in other words, what is that? Force times displacement. Well, remember, that's the equation for work. So the area of a force displacement graph tells us the work done. In this case, the work done on the spring. Now, to take this even further, if you notice here, this function here, when we take the area, that gives us a triangle. What is the equation for the area of a triangle? If you remember, the equation for the area of a triangle is 1/2 times height times base. Okay. So let's continue this down here. So work is is equal to 1/2 times height times base. But what is our height here? What is the height of this triangle from here to here? Well, that's easy. That's nothing more but, our force values. So, because we're plotting force on the y-axis, so height is equal to force. And in this case, the base of our triangle from here to here, the base is equal to displacement, or in other words, x. Okay? So let's keep going. So work done is equal to 1/2. Force. What is the equation for the force of a spring? We just said that. I'm going to write this over here. So the equation for the magnitude of the force of a spring is equal to Kx, the spring constant times x. So I'm going to take that and I'm going to plug that in for force, Kx, because that represents the force of a spring. Okay. So one more major thing we need to do here. You notice I have 1/2 times Kx times x. X times x. What is that? That is x squared. So 1/2 Kx squared. You notice this right here is the equation for elastic potential energy. Now, one more thing I want you guys to see here. If you remember, at this point right here, at point 0, the spring was not being stretched. So that means at this point here, that means we have 0 elastic potential energy initially. And of course, and then as we stretch the spring from this point to this point, we gave the spring elastic potential energy. So our initial elastic potential energy had to be 0. So I'm gonna write that here. So this represents this right here represents the final elastic potential energy of our system. Okay, and then that point right there represents the initial elastic potential energy, of the system. In other words, that point where the spring has no energy, no potential energy. So there you go. So that anytime you do work on a spring, you change the elastic potential energy of the spring. So that's our derivation there.